Well, good morning. Well, it's morning for me. And welcome back to CSC323 Programming Languages. Today, we are going to talk about subprograms. Now, that's an interesting term. What is a subprogram? Well, basically, what you call methods, or what we've been calling methods for the last 3 years or so, 2 to 3, well, 3 years, I guess, for most of you. That's an example of a subprogram. So in Java, we call the chunks of code that we give names subprograms. In Fortran, they can be called subroutines or functions. Sometimes they're called just routines. So there's a lot of different names, but the generic name for a method that you'd have in Java is a subprogram. So why have them? I mean, we've already just finished talking about control flow, and pretty much anything you'd want to do with a program, given basic data structures and control flow, you can do. So what's the advantage of a subprogram using subprograms in your programs? So I want to take a moment to see if you can think of some advantages, and then we'll talk about them together. Okay, so what are the benefits of subprograms? Well, we've got readability, through another name for subprograms is procedures. So we've got readability through procedural abstraction, right? If you see a method or subprogram that's called sort, and you pass an argument data, you don't have to think about the details of how that sort works. It just works if you call sort. So in your main program, you might have another method above that's called collect data. And you don't really have to think about the details of how that data is collected. You just say, there's a subprogram out there that goes and collects the data. When we problem solve as computer scientists, having this procedural abstraction is a really powerful tool that we use to manage the complexity of programs that we write. So there's a huge advantage to using subprograms because it lets us manage complexity. I'm sure you remember a time when you were a freshman, and maybe even now, where you got overwhelmed with how much work you had to do with a program. And this can happen not just with programs, but it can happen with a big problem that you have in your life. You can just get overwhelmed. And so how do you go about attacking a problem that seems insurmountable? Well, you have to break the problem up into smaller problems and work on those smaller problems. And that's what subprograms do. They're taking a complex problem, breaking it up into smaller problems, manageable chunks, and solving that manageable chunk. Okay, so readability is one tool, and I guess problem management as well. So there's a problem complexity reduction because we're breaking up into smaller chunks. Of the problem. Okay, so that's a huge advantage. A second advantage is reliability. Think about this, if you wrote some code and in that code you had a sort, and then a few lines later you had some more code that was the sort again, same sort, a few more lines of code, and then some more lines of code, and you had a sort again, If all three of these are the same, then you are suffering from something called copy-paste syndrome. If you are writing code and you're finding that you're copying the code and pasting it to solve another problem, then you are not using subprograms effectively. And what is the danger of copying and pasting? Well, the danger of copying and pasting is that you increase the chances that if you find a bug in this sort, that you'll only fix the bug in the piece of sort code where you're seeing the bug. So for example, if you find the bug in the sort code here, there's something wrong with the sort with a certain situation, a certain kind of data. Like let's say you're sorting names, and if the name has an accent in it, which might not be expected, like Saleh, all right, there's an accent there on the E. So if the name has an accent, the sort doesn't sort the name properly, all right? So then you go and you fix that here in this sort because you're focused on that particular sort. But the problem is you still have the bug in these two sorts. And they're not showing up at this moment because maybe those sorts are sorting a different set of data that doesn't have accents in it yet, but the bug is still there. So every time you make a fix to this sort, you need to make sure you make it to this sort and this sort. And you can forget. I mean, I'm only showing a few lines of code here, but there could be many lines of code between the two sorts, even though the lines of code for the sorts are the same. Okay, so how do you solve that problem? Well, if we pull this out, this sort out, and we put it into a sort method, sort subprogram, then when you fix the bug for the accent in the sort program, it'll fix it for the sort here, the sort here, and the sort here, because instead of having these lines of code, we're just calling the sort method. So reliability is a good thing. The other thing that it does is, well, I think that's good enough. I wrote down memory reduce. There is a slight memory reduction, right? The size of your program decreases a little bit, but I think that's fairly minor compared to the benefits of procedural abstraction and problem complexity reduction and the benefits of reliability. So, all right. So those are the benefits. Let's talk about a formal behavior of how a subprogram works. So subprogram has a single entry point. Basically the top of the subprogram. It has subprogram suspends the caller while the subprogram executes, although that's not always true, but for the most part it's true. And then it returns to the caller when done. So that's the behavior of a subprogram. Now what I wanted to do is show the anatomy of a subprogram. All right, so I'm going to write some code here. So this code is something that you might see in a C or a C++ program. But it's important because there are a number of languages that require you to have some additional sugar, syntactic sugar, to make a subprogram work. All right, so int sum, and it takes an array. Okay, semicolon. Now, that's a little weird, right? For those of you that are used to Java, this is somewhat strange. But let me explain. What you're looking at here is something that is called the subprogram declaration. So I'm gonna highlight this or call it out, and we're gonna say this is called the declaration. All right. And the next thing we're gonna do is we're gonna define the subprogram. All right, so the way we're gonna do that is we're gonna write the code for it. But we're actually going to repeat, it appears like we're repeating, well, we actually are, we're repeating the declaration when we do this. All right, so int sum, int array, square brackets, int size, open curly brace, some code that actually does the sum, return result, close that curly brace, and then we're going to call it down here. Okay, so this gets rather busy, but I'll try my best to make it so that you can kind of copy down the same notes here. Okay, so the first thing here, this part in here is called the signature. Now, the reason why it's called the signature is because it is possible to have multiple subprograms, sorry. So we could have multiple instances of sum that's the same name for the subprogram, but how do we tell the difference between one subprogram and another subprogram? The way we do that is we look at the signature. So what I mean is we could have a sum for an array of integers, but we also have a sum for an array of doubles. And when you make a call to sum in your code, the way the programming language knows which sum you're talking about is it looks at the signature. Okay. Now, this part from here to here has a special name. It's called the header. And finally, this part from here to here has a special name as well, and that's called the protocol. And then this entire thing from here to here is the definition. So now we have kind of a formal description or a formal labeling or anatomy. This is the anatomy of a subprogram. Fantastic. Okay. Cool. So that kind of takes care of kind of the introduction to subprograms. And now I want to get into some nitty-gritty stuff. This next part about subprograms is so important. So I feel like actually the next two sections are just super, super important. They're going to help you understand key elements of subprograms when you're exploring a new language. These are questions that you should be asking. So one of the fundamental questions that I always try to figure out when I'm learning a new language, and pretty much every language that I work with has some form of subprogram, is how does parameter passing work? Now already, I'm betting you're searching in your mind going, parameter passing, parameter, okay, I know, I understand how parameter passing works. You do for a couple of categories of parameter passing. But what you may not be aware of is that there are a number of types of parameter passing that you may not have experienced yet, but it's out there and you should I want to make you aware of it, okay? And also, I want to make you aware in a more formal way of all the categories of parameter passing. So when you attack a new language, you can say, oh, I know there's these different ways of doing parameter passing. How does this language do it? All right? So here is a call to a subprogram, and we're passing in a parameter P0. Now, what are the semantics? What are the semantics for parameter passing? All right. Another way of saying that is how, when we pass in P0, how does that parameter get passed in? Well, it turns out there's three flavors that you need to be aware of. All right. We have in mode. And what that means is we're going to get data from P0. We have out mode. That means we're going to put data to P0. And then we have in out mode. And that means we're going to do both in and out. All right. So this mode, I think you're familiar with in some fashion in Java, right? The default for Java for simple types is in mode only. You can only get data from a parameter. You can't put it, like if you pass in an integer, you can, as a parameter, you can get the value of the integer, but you can't really change it in the method and have that change reflected in the caller. If you have more complex types, you have something that's more of an in-out mode, right? When you pass in a complex type, the reference comes in. So the reference itself is an in mode, but you can use the reference to get access to data that exists outside of the method and manipulate that data, both reading it and writing to it. So it's kind of an in-out mode. But what you're probably not aware of is that there's this out mode semantic as well. So it's possible to have something that is an out only parameter. And that's a little weird. So I want to show you some examples of that. There are languages that let you do that, that you probably haven't experienced. So, and also there's ways that these semantics in mode, out mode, and in out mode are implemented. So this, what I'm talking about right now, are semantics, which is explaining the ways that parameters passing can work. But I'm not really talking about how, the mechanism that allows them to work, and that's what I want to get to. And so how are these semantics implemented? Well, it turns out that there's a few ways, and we're going to talk about those. So these are implemented using pass by, and then there's a couple of categories. So there's pass by value, result, value result, reference, and name. So I'm going to talk about each of these in turn and give you some examples to help you understand how they work. Okay. So let's start with pass by value. So pass by value implements in mode semantics. In other words, the parameter, we can get some information from a parameter, but we don't We're not allowed to change that parameter. All right. And so let's take a look at some C++ code that allows you to do pass by value. So here's a subprogram function method, whatever you want to call it, f, that has value as a parameter. And I'm going to increment value here. And I've got a little bit of code down here. I equals 42, f sub I, and then C out I. Okay, so if we let this program run, what will you expect for output from that C out? Take a moment, hit pause, take a moment to think about it. Okay, so what you should expect to see is the output here should be 42. Now, that might be a little bit surprising, depending on your understanding of how parameter passing works. So let's take a look at what happens. So I get set equal to 42, so I'm just going to write here I, and I now has the value of 42. Then we call the function f sub I. So when we call the function f sub I, a parameter, the parameter value gets a copy of the parameter value gets a copy of that I, so 42. And now if we execute the code, value plus plus, value goes from 42 to 43. But notice I did not change. And then when we return from the function f, we do a cout of I, and that prints out 42. And also value disappears. All right, so what I just walked you through is an example of something that is called copy value. So the way copy value works is we copy to the formal parameter. We have some overhead for that. And this can be a problem for large parameters. So that's the technique that allows pass by value to work. Now, I said it's a problem for large parameters. What do I mean by that? Well, there's no reason why you couldn't do something like this. Void f int square brackets value. And if, well, I don't think it's square brackets. I think you actually put in the size. So if it's int 1000 value, this will actually make a copy of the 1000 integer array that's passed in as an argument into value. So we're not getting a reference to value here. We're actually getting a copy of the entire array. Yikes. So that's an example of that problem. Okay, there is another way that these in-mode semantics can be implemented, and that's by a technique that's called access path. Now, the way the access path works is that instead of copying the integer I to the formal parameter value, we link value to the integer I. So we get access to the actual parameter. And then we, if the user of this pass by value parameter using the access path is just reading the value of the parameter. So they're not actually making changes to that parameter. Then the access path to the actual parameter works out really well, right? If our function f simply did this, void f int value, cout value, and didn't really do much else, then getting access through value to I without making a copy of I to value. So value is actually linked to I via the actual parameter. So let me show you what I mean by that. So value is a reference to I. Okay. And there's some syntax that hides the fact that it's a reference. Okay. So if we're just doing cout, this works out really great because using the reference to I, we just look at its value and we're good. We print out its value. If we do try to make a change though to the parameter, we'll trigger a local copy. So if we try to make a change to value, then what would happen is we'd break that access path link and we would keep a local copy. All right, so, and that would trigger some overhead. And that overhead is the overhead that would be associated with breaking the access to the actual parameter, creating some space for a local copy and allowing changes to be made to the local copy. So the access path works really well. It's very, very good from a performance standpoint if we don't actually change the parameter inside the method. Okay, cool. All right, so that takes care of our first type implementation of in-mode semantics. But let's take a look at another one. So this one is quite interesting, and it's one you probably haven't experienced before. This is called pass by result. So the way pass by result works is pass by result implements out mode semantics. So this is where we make a change to the parameter. So we're putting something to the parameter. But the key is we're only changing the parameter. We're not actually looking at it. So that feels weird, right? So let me give you an example of what that looks like. I think I actually have some code that shows it, and then we can talk about it. All right. Okay. So take a look at this code. So we have a method called getName. And what we're doing is the purpose of getName is that we'd like to get the first and last name of the user. So that's what this method is doing, all right? And actually, it's a really good example of where out mode might be useful. I don't know if you've ever experienced this before, but I find it incredibly annoying sometimes that you can't return more than one thing when you make a method call, unless you put that thing as an argument in a method. But in C-based languages like C and C++ or Java, when you pass that argument in, that argument can both be the argument that you want to have changed. That argument can both be read and written to. But really, in a method like getName, we don't want to read the value of name. It's useless in getName. The whole purpose of getName is to get someone's first name and last name. So we're making changes to first and last, but we're not actually looking at first and last. So if that's true, C# allows you to designate a parameter as out. So an out parameter is a parameter that can only be written to, it cannot be read. So here's the code that makes complete sense that would actually work with those out mode parameters. It says enter first name, then we're going to read the first name into first, then enter last name, and then we're going to read the last name into last. And then we return. And when we return, the caller gets the value of first and the value of last. And notice, nowhere in this code do we actually change the parameter first. I'm sorry, do we look at the parameter first or last? We don't care to look at it. We just want it to be changed. Okay, now look a little bit at the code just below that. So I have an example of sort of an abusive use of the out mode parameter. There's an attempt here to try to write out the current value of first, right at the beginning of the method. And that attempt would get flagged by the compiler. The compiler would say, whoa, what are you doing? You designated first as an out mode parameter. That means you can't read the value of first. And in this method, that makes a lot of sense, right? We don't care about what the value of first is or the value of last is coming into the method. We just want to populate first and last with a first name and a last name. So I hope that makes sense. So let's talk about how this is implemented. All right. So what we do is we treat I'm going to get rid of that. So what we do is we have two implementations again, both the copy value and the access path. All right, so here's how it works. So copy value. So we're going to create a write-only local variable in the subprogram. And then here's what we're going to do. At exit from the method, we're going to copy to the formal parameter. So for that first name, what we're going to do is we're going to create a local copy of the first name. And then at the moment we exit the getName method, we're going to copy the local value of first name back to the formal parameter that was passed in. All right. Now access path. That's the other way that we can implement this. Now the access path makes a lot of sense. We're going to access the formal parameter via an address or reference. And the parameter is marked as write only, so it's an error if you try to read from it. And changes to parameter are immediate outside the subprogram. Whoops. Okay. So I want to contrast that changes to parameter. So changes parameter occur, well, how do I say this? So changes to parameter, wait till exit. Changes to parameter outside the subprogram. There we go. All right, so changes to parameter outside the program, wait till exit. All right, for copy value, which makes sense, right? For copy value, we have a write-only local variable. And so as we're making writes inside the subprogram to the parameter, the stuff outside of the subprogram is not going to see those changes. We only get to see those changes at the exit outside the subprogram when we make a copy back to the formal parameter that was passed in. With an access path, though, any change you make to the parameter inside the subprogram is going to be immediately felt outside the subprogram. So if there was any parallel activity that was going on, you would see that. And yeah, cool. All right. So let's take a look at another form of semantics, and that is pass by value result. So pass by value result is kind of a combination of pass by value and pass by result. So this is an example of in-out mode semantics. All right. And let's take a look at, let's take a look at some sample code that would use that. So here's in P equals 42, and here's a call to a subroutine P. I'm going to end up moving this in a second. Oh, hang on a second. I see something kind of cool here that might be useful to talk about. Yeah, okay. Sorry about this. All right, I've got a little bit of code that I want to use to talk about pass by result one more time, just to show you, because I feel like we've got this cool, this good definition of copy value and a good definition of access path, but I don't have a good example that reinforces it. So I want to show you another piece of code that reinforces this. So let's get rid of that for a second. Okay. So let's look at an example that shows you pass by result and demonstrates the difference in behavior between copy value and access path. All right, so let's say I have a subprogram that looks like this. So it takes in 2 arguments. And then it says A equals 1 and B equals 2. Right, so it seems silly, but watch this, okay? So I say P equals 42, and then I say subprogram P. So notice what I've just done. I passed in P in 2 times, and P is in, and I've made these 2 parameters, A and B, out mode parameters. All right, so they're write only. And then I'm going to do a console dot write line P. So the question is, what is the value here of P? And it turns out, well, all right, I want you to try to figure out the answer to this, okay? So give it a shot, hit the pause button, and then come back in a few seconds. Okay, so it turns out, like many of the questions that I ask you in programming language, it depends. So the answer to what this value of P is depends completely on the way that the out mode semantics are implemented. And we have a copy value technique and an access path technique. So let's talk about both of those. All right, so I'm actually going to do the access path first. So if we use access path, what that means is that we have P with the value of 42, and then we have A, which is a direct reference to P, and we have B, which is a direct reference to P. So any change that we make to A is going to be made to P immediately, and any change we make to B will also make changes to P. So let's go through the program. So P is equal to 42, we call the subroutine, and now A is linked to P and B is linked to P. So we set A equal to 1, which means that P now has a new value of 1. And then we set B equal to 2, which means that P now has a new value of 2. So we're going to do a console write line of P, which is going to write out the value of 2. So that is going to be true if we use access path semantics. So this, I'm sure, makes some kind of intuitive sense to you, because we do use something similar to this in some of the languages you've experienced, where sort of you can think of this kind of like a reference to an integer. That's what A and B are acting like. They're acting like references to integers. Okay. Now, let's talk about the other way this could get implemented. So this is access path. Okay, the other way this can get implemented is by copy value. With copy value, we're creating a write-only local variable. So let's take a look at that. Copy value. So we start out with P having the value of 42. Then we create a variable A on the stack, and A is a write-only chunk of memory that is reserved for the moment that we exit. So A acts as a proxy for P while we're in the subroutine, and at the moment we exit, A will get written back to P. And B also is a write-only proxy for P. All right, so A gets set equal to 1, so we have a local copy of 1. B gets set equal to 2, we have a local copy of 2. And here's what's interesting. What is the end result? At the moment that we exit, both A and B are going to be written to P. The question is, what is the order that that happens? Because that's what's going to determine the actual value of P. And when you pull stuff off the stack, which is where these local variables are stored, they get pulled out in reverse order of being declared. So B will first write to P, and now that 42 becomes a 2. And then A is the next thing that gets pulled off the stack. We'll write to P, and so that 2 becomes a 1. And so if we're using copy value, the value that ends up in P at the end is going to be 1. So that's pretty crazy. So depending on which of these two mechanisms implement the out mode semantics, you're going to get different results. So that is really, really important then for you to understand, if we're using out mode semantics, what are the what's the way that it's been implemented in a particular language. Is it copy value or access path? All right, cool. All right, so now we're ready to move on to pass by value result. So the way that pass by value result works is we're going to use in out mode semantics. And typically, the way this is implemented is using an access path. And it's used to access the actual parameter. So you can sort of think of this as passing by reference, which I'm going to talk about that pass by reference in detail in a second, but we've experienced that in lots of programming languages already. Unless two subprograms access parameter at the same time. And then it does copy value. Okay. So in a way, the example that we have right here, even though this says it's out only, demonstrates how this might work. So actually, well, I'll just write a little bit more code to give an example here. So let's say we have void sub in out int a and int, and then in out int b, and then we say a equals 1 and b equals 2. Okay. Now, if we call sub, and let's say we have an int p equals 42 and q equals 52. Okay, so if we call sub pq, then the way this is going to work is we're going to use an access path only. A gets set equal to 1, and so A has a link to P, and so it will just change P immediately to 1. B has a link to Q, and so it'll change Q to 52 immediately using an access path. All right, but if we did sub PP, we're back to basically that out mode example up here. And what's going to happen in this situation is that instead of doing things by access path, as soon as we determine that both P's, both A and B are linked to P, and we see that A is making a change to P, we're going to do things by copy value. And when we do things by copy value, it means that the end result, the end value of P, is dependent on the ordering of how these local copies of A and B are placed in the stack, just like this example that we did up here. The only difference between this example up here and the code that we have down here is that in this example, you're either doing copy by value or access path. But in this example, pass by value result, you're doing access path by default until you see that there's a conflict, because you have two parameters that are both linked to the same piece of data. And when that happens, you switch to copy value. All right, cool. So that takes care of pass by value result. The next one that I want to talk about is pass by reference. So this is back into familiar territory. All right, so pass by reference is another way of doing in-out mode semantics. And let's just do an example of some code. So void f int ampersand a int ampersand b, a equals b minus 1. All right, and then I'm going to say down here, list sub 10 is equal to 5. And then I'm going to say f list sub 10 list sub 10 cout list sub 10. Okay, so the question is, what do we end up with a value here? What value ends up here? And the answer is, let's do a little model of how this code is implemented. So first of all, in-out semantics are implemented using access path. No copy value. All right, and so how does that work? Okay, so let's take a look at list sub 10. So here's list. All right, and list is a reference to an array. All right, and right here, we're going to say that this is position 10 in the array. And at this point, that 10, when this line gets executed, that 10 has a value of 5. All right, now we call f with list of 10 and list of 10 passed in as arguments. So how does that work? Well, A gets an access path to 10, and B, or list of 10, and B also gets an access path to 10. And using a little bit of syntactic sugar, that ampersand in front of A and B is used by C++ to say, these are references to integers. They're not actual integers, but we're going to treat them syntactically like actual integers inside the code. It's kind of a cool little piece of syntactic sugar. All right, so when we say A equals B minus 1, well, A is going to be set equal to the value of this expression, B minus 1. Well, B has the value of 5, because we're looking that up in position list of 10. Subtracting 1 from that is going to give us 4. And then A is going to be set to 4. So this 5 becomes a 4. All right. And so now we return from the method. And when we return from the method, we're going to see out list of 10. And that's going to give us the value of 4. All right. So one last way of doing parameter passing that is somewhat funky. All right. And that is something called pass by name. Oh, you know what? I should just make a mention here. I forgot about this, but it's in my notes. So pass by value result, kind of weird, but of course you know it. Fortran, it's how Fortran does parameter passing. So just be aware of that. Okay, so let's talk about our last way of passing in parameters, and that's called pass by name. So the way that pass by name works is really funky, and I just want to give you an example to explain it, and then you'll get it. All right, so I'm going to write some code. This is not how C-based languages work, but it does demonstrate the idea of pass by name. Okay, so we start out with a subprogram definition. And then adjacent to that subprogram definition, we make a function call f length width. And then what happens is that at compile time, the compiler looks at this function call f length width and then looks at the function or the method itself, the method definition, takes those two, combines them, and creates a brand new method with every instance of length linked to the parameter A substituted in the method call, and every instance of width linked to the parameter B substituted in the method call. And so we end up with a brand new method that the compiler creates that looks like this. Void f int length int width length equals 5, width equals length times width, end. Now, that's pretty funky. And actually, sometimes when I teach the freshmen about how methods work, this is how I show them how methods work. In other words, they see this abstract method, and I'm trying to teach them how to connect the abstract method to a method call like this. So I just substitute the parameters in and say it's sort of like this, but not really. But pass by name is actually taking each variable, length and width in this example, and rewriting the subprogram with those variable names. And those variable names are linked. They're actually linked to the actual variables length and width. So anytime you make a change to length here, you're making change to the length here as well. Anytime you make a change to width here, you're making a change to the width here. This is pass by name implements in out mode semantics. Now you might be wondering, hey, do languages actually use this? And the answer is yes, they actually are used in some languages. So I wrote down a specific language. It's pretty old, but it's just proof that it's out there. So Algol 68 is an example of a language that uses pass by name. Well, that finishes our introduction and our discussion of parameter passing. The next thing that we're going to look at is how subprograms use the stack to work, basically. And so stay tuned for that.